Next lecture we will be looking into solutions to some of the classical synchronization problems. But before we do this, we would like to understand the concepts of deadlock and starvation. So these are important concepts in synchronization. What do we mean by a deadlock? Well, we will just illustrate it by an example. So this is an example that shows this is the simplest example for explaining deadlocks. A deadlock means two or more processes are waiting for each other. And they're waiting for each other forever. So if we have two semaphores, S and Q, and we have two processes, 0 and 1, if process 0 does wait on semaphore S, then it does wait on Q, then it does some critical section code, then it signals S, signals Q, and P1 does it in the other order, in the reverse order. It does wait on Q, then wait on S, critical section, signal Q, signal S. Now, here, there is a possibility of a deadlock, of having a situation where the two processes are waiting for each other. How can this happen? So give me a specific scenario under which, in which the processes will end up waiting for each other. So yeah, a specific scenario or an order for the execution of these waits and signals. Yeah.
You call wait S, and then P1 calls wait Q.
Yeah, exactly. So if P0 waits on S, so initially both semaphores are initialized to 1, so an instance is available. So P0 will find an instance and it will lock S. But before it waits on Q, here, it gets interrupted, it loses the CPU. And P1 does a wait on Q, right? So now P0 has S and P1 has Q. But P0 will be waiting for Q, and Q will only be released by P1. P1 will never release Q, because P1 will go into the waiting state, waiting for S to become available. And P1 will be waiting forever, because P0 will never release S, will never signal S, because P0 is waiting for Q, and Q is held by P1. So each process is waiting for a resource that is held by the other. And both will be waiting forever. So there is no way out of this except for terminating processes, or we will see. We will talk about deadlocks, how to resolve deadlocks later. But this is waiting forever. Two processes waiting for each other, or multiple processes waiting for each other. Now, starvation. I hope that the concept of starvation was clear in the previous lecture. In the previous lecture, we introduced starvation as the opposite of bounded waiting. If waiting is unbounded, then we have starvation. So who can describe the concept of starvation and how it differs from a deadlock? So last lecture, we gave examples. We gave a solution in which starvation cannot happen, and an example in which starvation may happen. So what was the example in which starvation cannot happen? So we gave a Peterson solution. And we gave a solution for the critical section problem using test and set. How could starvation happen in the solution that we described last time for the test and set? Okay, so this is test and set. So starvation could happen if a process gets into the critical section, unlocks it, but keeps the CPU, and then executes the next iteration of the loop, and locks the critical section again, and keeps doing this for an unlimited number of times. Now, how does this differ from a deadlock? Conceptual, how does this differ from a deadlock?
There's still progress being made in one of the processes, even though the other one's not making progress.
Okay, so that's one important difference. Yes, so one process is making progress, but the other process could be starving. Now, starvation is something that in practice, it doesn't mean that a process will never get the resource. It will eventually get it, but after waiting for a long time. Now, starvation means that we're not setting a limit on the number of turns that this process will get on the critical section while another process is waiting. So there is no limit. You know, we're not saying that this process cannot have the critical section more than 5 times or 10 times or 100 times. There is no limit. This is what starvation means. Right? So even if we say that, you know, if we somehow modify this solution such that there is a limit of 5 times, that won't be starvation. As long as there is a limit, it's not starvation. So what was the limit in this solution? How many times can a process get the critical section here while another process is waiting?
Once.
Yeah, so the limit was 1. Why?
Is the waiting I equals true and the key equals true is going to yield it to the other one. If the other one's also waiting.
How was it yielding? So the point here, the idea here was that a process, when a process is done with the critical section, it's going to check if there are any waiting processes, and if there is a waiting process, it's going to give it the critical section. So that's a solution that avoids starvation. Okay. So the concepts of deadlock and starvation are extremely important, and it's extremely important to understand the difference between the two. So the deadlock is hopeless and there is no progress made. Starvation is one process could be making progress while the other process is waiting for a long time, and normally it's not going to be waiting forever. You know, in practice, it's not going to be forever. It's going to be for a long time, but not forever. So it's not hopeless. Priority inversion is a totally different concept. So let me see if I can explain this. So this is a totally different concept. Suppose that you have processes L and M and H, where L is a low priority process, M is a medium priority process, and H is a high priority process. Now the scheduler, you know, as we will see when we get to scheduling, and we say lots of things about scheduling before we get to scheduling in this course. But one of the things that the scheduler does is assigning priorities to processes. So when the scheduler assigns a process high priority, it does that because it wants that process to get a lot of CPU time. It wants it to get priority, and it doesn't want it to be waiting for lower priority processes. Now, what if we have the following scenario? We have a lock, X. So this is process L. Critical section unlock, X. And suppose that the lock is currently available, and L arrives and locks it, and L is in the critical section. While L is in the critical section, process H executes a lock, X. Now, if H attempts to do a lock, so H is here and L is here. Then the lock is taken by L, and H will be waiting, which is fine. So far, it's not that bad. H is waiting, that's fine. L will eventually complete the critical section, and H will proceed into the critical section. Now, what if process M becomes ready? If process M becomes ready, the medium priority process becomes ready, the scheduler is going to give the CPU to M. So M has the CPU. And L will not have the CPU, assuming that there is a single CPU. So L has the lock, but doesn't have the CPU. So it's just waiting, because it's waiting for this, it's in the ready queue. So L now is in the ready queue. H is waiting. And M is running. But with M having higher priority than L, M will keep getting the CPU. And L is not getting the CPU. Now, that's fine. You know, L waiting for M, that's fine, because that's the intended behavior. That's why M was given high priority. But the unintended behavior is having H wait for M. So at this point, H is in the waiting state, M is in the running state. So the unintended behavior is H, now the high priority process waiting for M. So this is priority inversion. This is the, this is the opposite of what was intended when H was assigned higher priority. So this is priority inversion. Now a solution to this problem is to note when H arrives and becomes waiting for H, now the system notices that there is a high priority process waiting for X. So the process L that has the lock will temporarily have high priority. So the system boosts the priority of L temporarily to high priority while it's in the critical section, so that it doesn't lose the CPU when it's in the critical section. And then it completes its critical section. And when it's done with its critical section, the system is going to change its priority back to L. So the system will temporarily change the priority of this process from L to H while it's in the critical section. Why? Because if you are holding a lock that a high priority process is waiting for, then you are temporarily a high priority process. Then once you release the lock, you will go back to your normal priority level. Okay? So this is what we call priority inheritance. Priority inheritance is a solution to the priority inversion problem.